Hello, I'm Eric, K7RKU, and we're going to talk today about battery box design and construction. Welcome to the channel. Let's get going. All right, we'll talk a little bit about battery box design and construction. So the first question, of course, is, why build a battery box? Well, because we all like things that run on electricity, of course. We're talking about amateur radio equipment for recreation or emergency, medical equipment like CPAP when the grid power is not available, either when you're away from home or if there's an emergency and you need to stay healthy while the emergency gets resolved where you ordinarily live. Computer or tablet charging, mobile phone charging, power for light source, fan, or whatever else. Well, then should I just take along a battery? Well, yeah, certainly if your power needs are very simple. A battery can only supply a single device unless a power distribution setup is added. Then maybe a battery box? Yeah, definitely. That is your best bet. It powers multiple devices simultaneously, and it combines power distribution, wiring, and connections in an easy to transport package that protects the wiring and connections from damage. Well, should I just buy a battery box? Well, no, I think you're better off learning as you build a battery box and getting exactly what you want. Prefabricated battery boxes are, by definition, limited with regard to connections, power capacity, and features. So if they make 3 different battery box designs, if you want one of those 3, you're in luck. If you end up getting more than what you wanted, you have some wasted ability there. If you don't get it quite as much as you want, then you're not getting what you really need or want. So let's talk about designing a battery box. We'll cover a little outline here. First thing, of course, is choosing a battery. We'll talk about the type of the battery and how big the battery needs to be. In order to determine the size of the battery that's needed or the capacity of the battery that's needed, we'll talk about calculating individual loads for the different things that you want to power with the box, calculating combined loads if you want to power more than one thing at a time, and some other factors that affect needed capacity. We'll also talk a little bit about designing your circuit, starting with general considerations, and then going down to sizing of the wire, choosing power connectors, possibility of adding a battery shunt, which I did in my project. We'll talk a little bit about choosing an enclosure, and then finish with some general construction tips. So the first thing is, what type of battery should you choose? Well, there are several that are commonly available. LiFePO or lithium iron phosphate batteries. They are probably most commonly used in battery box construction. They have, we're comparing these to lithium ion batteries. Lithium ion batteries are typically found, for example, in a cell phone battery or a laptop computer battery, these kind of things. And then lead acid batteries, which you probably have in your automobile as your car battery. So self-discharge is basically a spontaneous loss of power without a load applied. It is lowest among the 3 types of batteries in a LiFePO battery. Usable temperature range for the LiFePO batteries is excellent, minus 4 degrees Fahrenheit to 140. I hope never to be beyond those limits myself. Charge lifespan, there's a pretty significant difference here. And if you notice, lead acid batteries are really poor in this regard, and LiFePO batteries are great, far better actually than lithium ion batteries. Tilting of the battery or use in a rugged environment, LiFePO batteries, no problem. Lithium ion batteries, no problem. Lead acid batteries, yeah, potential problem. They don't like to be tipped, and certainly they're not designed to be used upside down. And I think probably the most important difference between the different battery types is the usable portion of the charge that the battery holds. So if you had a 40 amp hour, lead acid battery, you could use about 50% of that charge. So what you really have is a 20 amp hour usable battery. With a LiFePO and lithium ion batteries, in theory, they're able to be discharged completely, right? So you get 100% of that charge. Now, some manufacturers recommend that you only discharge it to about 20% remaining capacity, because it does extend the lifespan of the battery. But if you're in a pinch, like an emergency situation, well, you can use the whole thing. So I think, at least from what I can tell, LiFePO is for sure the best battery option for a portable battery box. All right, let's talk about calculating individual loads. We'll use an example, which is a Yaesu FT991A. This is an amateur radio transceiver, and it's honestly one of the kind of bigger, heavier ones. It has a lot of nice features, but it is really not so much designed for portable operation. In any event, that's what I have, so that's what I calculated in for my design calculations. Now, the lowest anticipated power need would be low power CW or Morse code receipt and transmission, meaning 5 watts of transmitting power or less. If I'm receiving a signal and there is a signal present to be listened to, the transceiver uses about 2.2 amps. If I'm transmitting at that low transmitting power CW, it's about 7 amps. The typical duty cycle, meaning the typical amount of time that's on versus off for transmitting and receiving, would be 80% receiving and about 20% of the time transmitting. So for this calculation, we would take our 80% times the 2.2 amps that it would take to receive. That's 1.8 amps. We would take our 20% of the 7 amps that it would take to transmit, and that calculates out to 1.4 amps. We would add those together for a total of 3.2 amps. Now, sometimes amateur radio transceivers are used in a more vigorous or more rigorous setting where you're transmitting a lot in a contest, for example, or with field day, where you're trying to make a lot of contacts as quickly as possible. If you change the calculations as we've indicated below, your end result would be 4.6 amps of power required. All right, so the highest anticipated power need would be high power telephony, in other words, voice transmission. For receiving, would be 2.2 amps, and for transmitting at that high power would be 23 amps, pretty high load. So again, with the regular duty cycle of 80% receiving, 20% transmitting, that would calculate out to about 6.4 amps of draw. For more vigorous or aggressive transmitting setup of 50-50, it would be about 12.6 amps. All right, so for example, if I'm using a 40 amp hour battery, I should be able to run my FT991A at 5 watt QRP-CW, in other words, low power Morse code transmissions, for 40 amp hours divided by 3.2 amps equals 12.5 hours at a typical 80-20 duty cycle if the battery is the only thing drawing power from the, if the transceiver is the only thing drawing power from the battery. Again, assuming a 40 amp hour battery, I should be able to run the same transceiver at a high transmitting wattage for 40 amp hours divided by 12.6 amps equals 3.2 hours on that higher demand, higher wattage transmission and more transmitting time cycle. All right, let's do a little different example here. One of the other things that I wanted to power was a CPAP, right? So it's a device that assists with breathing at nighttime for folks that have sleep apnea. So this particular one is called the Philips DreamStation, based on the findings of another YouTuber, which I've linked below with the QR code. This device draws about 0.54 amps. All right, so if I am using a 40 amp hour battery, I should be able to run my DreamStation for 40 amp hours divided by 0.54 amps equals 74.1 hours. Presuming that I'm running it for an 8-hour sleeping time, that would last me 9.3 8-hour nights or 9.3 days if the device is the only thing drawing power from the battery. All right, so what about if I want to run more than one thing at a time, calculating combined loads? Yeah, so how about if I want to use my radio some amount of time during the day and then use my CPAP at night? Great. Okay, so when we're powering multiple devices, we add the amps required by each device and then continue with the calculations described previously. All right, so for example, if I am using a 40 amp hour battery and I wanted to run my FT991A at a low power CW on a lower intensity cycle, like 80-20, for 4 hours each day, and my DreamStation device, my CPAP device, for 8 hours nightly, that would add to 3.2 amps times 4 hours per day, plus 0.54 amps times 8 hours per day, and that would equal 12.8 amp hours per day, plus 4.3 amp hours per day, for a total of 17.1 amp hours per day. I should therefore be able to power that combination of loads for 40 amp hours divided by 17.1 amp hours per day equals 2.3 days. All right, now there are some other factors that affect needed battery capacity. First is power waste. Power inverters, which are devices that convert DC battery box power to AC power, are components that are sometimes included in battery boxes, and they have an inherent power wasting tendency, right? So they generate, some heat is generated in that conversion of DC power to AC power, and the heat comes from energy that doesn't make it through to the other end of the inverter. To make this, to take this power waste into account, you need to determine the AC power production that you are trying to accomplish and figure out how much DC power is required to produce that amount of AC power. You might be able to discern this from the inverter documentation or querying the manufacturer of your inverter device. You would then use that DC power figure in your battery capacity calculations. All right, how about power generation? Yeah, some people add a solar power source that charges the battery box. In other words, contributes charge to the battery box instead of taking it away. In so doing, they're creating what's called a solar generator. And in that situation, you would subtract the expected power contribution of the solar component from the combined load power demands before you do your battery calculations. All right. Now, addition of a solar power source requires both a solar panel and a solar charge controller. Scan the QR code below for an excellent overview of how to accomplish this with some nice pictures, part numbers, and a clear explanation of how it all works. All right, now there's also an overbuild factor, and certainly I did incorporate this with my battery box. Basically, this is essentially a safety factor. For example, if you determine whatever battery capacity you feel is the best, and you feel that you want to add an overbuild factor of, for example, say 20%, you would then multiply the amp hours that you had calculated previously by 120% in this case, because we're trying to do a 20% overbuild factor, and that would give you a result of a need of somewhere around 28.8 amp hours or greater. All right, let's see, designing your circuit, general considerations. All right, perfect. So there are a number of different general strategies that people use to build battery box circuits. So the example that we'll give later uses this first approach, which is going from the power source, which would be the battery, through a high amperage fuse to a fuse panel, and then from there to individual power draws. Another option would be going from the power source, the battery, through a high amperage fuse to red and black post connectors, and then wiring through an individual fuse and out to each individual power draw. Another option would be to start from a battery, the power supply, go to red and black post connectors, out to individual fuses, and then on to individual power draws. Now, this sounds like the second one I said, but there's a pretty important difference. If you notice, in this third option, the post connectors are not fused, which is not recommended. Recommend that you use fuses. It's just safer and it makes more sense. Lastly, it's conceivably possible that you might just say, well, I'll grab a battery, a power source, I'll just splice everything together, and then I'll run that out to the individual power draws. This is really a bad idea. As you notice, nothing is fused here, so certainly not recommended. All right, so as you can see, there are a number of approaches to battery box wiring, and the approach that I've described, that I am describing below, makes the best sense to me. I think the most important parts when you design your battery circuit is firstly safety, and then secondly ease of troubleshooting should a circuit issue arise. The benefits of wiring each individual draw circuit to a common fuse panel is that the fuses are located centrally. If a fuse blows, it's real easy to tell which fuse blew because you're looking right at all of them. All of the fuses are a common type, automotive fuses. They're readily available and inexpensive. There's a logical wiring layout that facilitates troubleshooting should an issue arise. Next question is, some authors have said, hey, you really need to put a high amperage fuse in the main circuit of your battery box. Some people feel like, well, I don't think it's really necessary because lithium batteries typically have an integrated protection circuit that should open the circuit or disconnect the battery in the case of a short circuit. Now, the argument for including a high amperage fuse in line with the main circuit is that even if this is true that there's an integrated protection circuit in the battery, redundancy seems like a pretty good idea. And if the protection circuit in the battery failed for whatever reason, the consequences, and you did not have a fuse, the consequences could be pretty catastrophic. Fire in your tent, RV, your car, garage, closet, whatever, or damage to the expensive battery. So from my point of view, a high amperage fuse between the battery and all the loads of your battery box is cheap insurance and highly recommended. All right, some detail stuff. Sizing the wire. So sizing the wire is pretty straightforward. You just need to make sure that the wire that you use for a given circuit is large enough to handle the current that you expect to travel through that circuit. Wire that's too small creates resistance, which can generate heat and cause a drop in voltage. There are guides for which wire to use for a given current are readily available. There's a good one if you scan the QR code in the image below, or you could simply search 12-volt wire gauge to amps on Google or whatever your favorite search engine is. All right, so choosing power connectors. How do you decide what kind of connections do you want to have on your battery box? Well, I think it's important when you're making this decision to anticipate obviously your current equipment, but also any equipment changes that you foresee. In other words, if you think, I may buy a QRP rig that may not require as much power. I may, get a bigger rig or something that additional that may require power. Or you may find yourself planning to operate in different settings. Maybe I want to haul this thing up a mountain instead of just, pulling it into the local, state park to do POTA. Next thing is I would encourage you to include some power pole connectors. Certainly they are the standard for powering amateur radio equipment at this point. Recognize that future devices, next year's iPhone or the year after that, much more likely to use USB-C than USB-A connectors. Consider special needs such as a cigarette lighter power adapter, which might be needed by medical or other equipment that you want to power. And remember that you may want to share power with a friend or buddy. So make sure that you have enough connectors to allow for that. All right. In my project, I added a battery shunt, which may be something you're not familiar with. Basically, what it is it is a device that's in the main section of the battery circuit that provides important battery information via Bluetooth to a smartphone app. So the app tells you things, real-time information such as battery voltage, current, amp hours consumed, state of charge, and battery time remaining. It also gives you some historical battery statistics. So, from my point of view, it's basically like a gas gauge, if you will, for your battery. If you were to embark on a long trip, you probably would be pretty nervous if the gas gauge in your vehicle wasn't working. I feel the same way. I want to know about how much I have left. If I need to budget, then I can do so as long as I understand where I'm at. So next, we'll talk about choosing an enclosure. There are some battery boxes have been built in Pelican-style cases. These are the heavy cases that I'm sure you've seen. They are rugged. They are waterproof until you drill holes in them. They come with a configurable foam, although that may actually end up being a little more of a liability than a benefit. They are heavy. They come in multiple colors from multiple manufacturers, and there are different price points, all the way up to the big name brand ones like Pelican cases down to like, hey, I got it at Harbor Freight. They have a high-end appearance, which can help you look your best, shall we say. Then there's the ammo box or field case. Now, rather than the old metal ammo boxes that we used to buy at the Army Surplus Store, we're generally talking about plastic cases here. They're substantially thinner than the Pelican-style case. They are rugged-ish. They're pretty rugged. They are water-resistant if it has a rubber gasket around the lid. They're inexpensive, typically. They're lightweight. They're easy to drill, which is a very nice practical consideration. They come in a bunch of different sizes, all kinds of different colors from different manufacturers, and there are different price points. Let's talk about some general construction tips. All right, so when you are looking down into the box with the lid open, which is basically how you're going to build your battery box, it's easy to forget that the lid's going to be closed most of the time. So you got to make sure that whatever you're putting in the box works fine and fits with the lid closed. You might consider making a simple cardboard mock-up of a potential enclosure to see if your components will fit. There are a ton of different field cases, ammo boxes. And some of them vary only minimally in terms of dimensions, but that minimally can be a pretty big deal when you go to try and fit your things in. I recommend that you get the inside components that you want to place, whatever connectors, whatever, if you choose to use a shunt, whatever battery you choose, get those first, and then figure out, okay, what is going to be a container, if you will, that will fit these things that I want to fit in there, would give me enough room to work but not be excessively large. I'd encourage you to walk through the assembly process in your head before drilling to anticipate any spacing or clearance issues that might arise. So next question is, well, how did my build turn out? Yeah, actually, here's the statistics on mine. I used a 40 amp hour LifePo battery from Bioenno. I furnished it with power pole connectors, USB-A connectors, USB-C connectors, and a cigarette lighter adapter. The weight of my box is this. The battery itself weighs about 10.4 pounds. It's a big battery. The enclosure weighs 4.9 pounds. That includes the shunt and all the connectors and so forth, and for a total of 15.3 pounds. So, it's not lightweight, but it also generates a lot of power, or holds a lot of power, I should say. Mine has some extra features which were valuable to me: an LED utility light and the battery shunt so that I can gauge remaining power. And so overall, my battery box was a good fit for my needs, with abundant power and manageable weight. My typical use would be to drive to a state recreational area, national forest or whatever, and then carry my battery box for the 150 or 200, 300 feet from the vehicle to the the setup site. I'm not going to be lugging this thing up a huge peak. My battery box has all the features that I want and none of the features that I don't want. And most importantly, I learned a lot putting it together. So I'd encourage you to consider trying your hand at building a battery box. So thank you, and we'll show next a little bit of footage from the actual construction of my battery box. All right, here are the components for our battery box. We have the box itself, which in this case is a 50 caliber field box, basically. And this particular model has a little opening where you can mount components and then close it to cover them, keep sand and dirt out, pretty handy. And then, of course, the box opens and it's a regular box. Now this particular one, it does have a gasket, so, a little bit of extra protection against the elements. That's worth something. Next is the heart of the project, which is our battery. This is a 40 amp hour Bioenno battery, and I never really intended to buy such a big battery, but I got a really good price on it from the Chameleon Antenna folks who also sell these batteries. So it's a 40 amp hour battery and lithium iron phosphate. We have several plugs that we're intending to put in. We have some high wattage PD plugs and a QC USB A plug. The PD plugs are USB-C, and the reason that I got those was because I can charge my Mac, I can charge my GoPro, I can charge my iPhone, of course. Next to that, we have the cigarette lighter adapter, and I use that for my medical equipment that I use at nighttime. Next to that is a double 35 amp Anderson power pole plug. We have in the background a fuse, I guess, I don't know what you call it, a fuse, not a fuse box, but a fuse panel that will run separate circuits for each of these things that are going to consume power in our battery box. We have a light just for usefulness. This particular one has a high brightness and a low brightness, hence the different wires coming out, and of course it has a wire for the neutral or negative. We have a 2-position switch that we'll use to control the light. This is a shunt, and basically it's going to act as a fuel gauge for our battery. In other words, it's going to tell us how much battery charge is left. I have one that I've used on a previous project. It worked great, and I thought, you know what? I want to know how much charge I have left for when I'm out camping and need to use my medical equipment at nighttime and so forth. This is a 10 gauge 40 amp fuse that we'll put in line with the main battery positive. This is an extra 50 amp power pole adapter that I purchased because the battery comes with two options. One higher voltage with heavier cabling, and one, amperage with heavier cabling, and one smaller cabling with a smaller amperage rating. So I thought, I'll use the big one. We have some 16 gauge wire, just basic Amazon stuff, some 10 gauge wire that I'll use for the main circuit, and we have some Velcro that I'm intending to use to try to get the battery to stay still in the box. We'll see how that works out. And that is our collection of parts. One of the problems that I encountered as I was creating this box is trying to figure out what size ammo case or field box or whatever to order that would fit the interior parts that I had already chosen or determined. So there are a lot. Some of them are, you know, a 5/8 of an inch off from the competitor's brand, and sometimes that 5/8 of an inch can make a really big difference. I made this model out of some cardboard that was laying around, right? So I chose to mock up the usable dimensions of a particular field box. This one that I had mocked up was earlier in the process, and so this does not match the box that I eventually ended up getting. This one proved, in my estimation, to be a little tight. So in any event, you know, the idea would be to stick your parts in it, and as you can see, this one is, you'll see subsequent in the video, this one is quite a bit smaller than what I think I really need. We're talking about trying to put the fuse panel in, so that would be, you know, not impossible, but reasonably snug. But the big hurdle would be, you know, trying to get this in, and that's quite close. And we need a little bit of jiggle room, right? So if I'm mounting this with Velcro, I'm gonna have to go, you know, right to get it out, and I don't think I'm gonna have that jiggle room to get the battery. I don't think I'm, you know, strong enough to just grab it and just, you know, hulk it out of there. So in any event, this is a good tip if you are a little bit OCD like me, then mocking up your field case size or ammo box size can be a useful tip. Okay, we'll talk just a little bit about some construction specifics, you know, basically how to make sure that everything kind of works okay in the end, we have room for everything, and that it looks nice. So I'm a symmetry guy, so that's what we'll try to accomplish for this build. Now, we could, I guess, measure through this, but if you notice, the hinge is symmetric, and I think we can probably reliably count on the manufacturer made these, you know, centered it on the box. So we will center, and I presume that this post is in the center of our panel, so we'll essentially put the post so that it lines up with the center of that hinge. And let's see here. Okay, we're gonna get started. I've picked a drill that's about the same size, well, that is just a little bit larger than the screws that we need. I'll go ahead and feed it through. I found a spot that I like. We're gonna start with this hole here. Great. Now, what we'll do is we're going to turn the box around, and we will line up this hole that we've drilled. We'll get the fuse box square. In other words, you know, centered, balanced, whatever. Looks like that might be a better option. Okay, great. So this fuse box, I think, or this fuse panel, I think, is symmetric, but we're going to then drill this way, and we're not planning to place the fuse box on the outside of the box, but we're going to use the screw holes as a template so that when we go back to the other side of the box, it will fit. Okay, so we have our 4 holes for the fuse panel, and I have drilled 2 additional holes where I wanted the light, so we're good there. Now this particular light, it has kind of a thicker section that sticks down. This will protrude through the gasket or rubber fitting that came with the light. But we want to make sure that, you know, we're not going to get stopped at the case. So we're going to go ahead and drill this hole. And remember, we have this entire thing. So if we drilled like a 1-inch hole, we'd be fine. It's still going to be covered. We're not going to do that. We're going to try to match this. and we're going to use a step drill for that. Now, I just measured this from the center of this hole to the center of this prominence is about 2.5 inches. So we'll go ahead and mark that. All right, we've now chucked our 3/16 bit. We're going to find our mark, and we talked about drilling just a little bit below, so we'll do that. Hold on just a moment. Here we go, and we're off to the races. Okay, so I measured the diameter of that prominence from the light. It was around a little less than 1/2 inch. We're going to go ahead and measure and drill to 1/2 inch. That is, this is going to go in the hole, so that'll be the 1, 2, 3, 4, 5th stop. So here we go. I believe that'll do. Okay, perfect, great. So yeah, we'll get that passed, and then this one through, great. And we are just about there. Okay, so we have gotten our light mounted. We have driven the screws for the fuse panel. As you can see, we have nuts and that we have used basically as spacers. And here we have our wires from the light, free moving, no problem at all. So we should be in good shape. Okay, so we've moved on to placing our power draws, right? The USB ports, the power works, connectors, and so forth. Did some measurements, did a little math, and I have spaced them evenly, and we used our square to get it nice and centered. So what we'll do is our step drill, the initial piece of it is a 1/4 inch. So we'll drill with a 1/4 inch drill, again, just for a little better control. And then I have applied some blue tape around the drill so that I can stop at 1 1/8 and not overbore the holes, because that's going to ruin my whole day. So we'll get going on that. Notice that I have the lid open, otherwise I would have probably just drilled right through the lid, and that also would be frustrating. Okay, here's an example of drilling one of the holes. And this is a big bit, so I kind of like going reasonably slow with it, but obviously, you know, whatever works in your hands. Okay, so one note of interest, I'm getting ready to mount this shunt here on this side of the case. And what I discovered, or realized I guess, is that I'm not going to be able to get my screwdriver or my you know, wrench thing in here very easily because of the width of the case. Now, over here, as long as the battery's out, I've got pretty clear access to the fuse panel, and that's very useful because there's a lot of screws and stuff that needs to be, you know, instrumented or you know, loosened and tightened on this. This I can work around. I happen to have a little tiny ratchet socket, and so I'll be able to tighten it up with that. But short of that, yeah, that would be a drag. So definitely when you're planning for which side of the box you want to put what things on, remember that it is going to be difficult to get tools such as a drill or a screwdriver socket, whatever. It's going to be more difficult to get it in the short dimension of the box than it will in the long dimension of the box. Okay, so we're ready with this, so I guess you might call it supply side cabling or primary cabling, however you want to look at it. So in the event, this will attach to our 50 amp connector on the battery. The hot side, the positive side, will go through this 40 amp fuse and then connect to the positive pole of the fuse panel. This is the little minor positive power supply that's needed for the shunt. The negative cable will run to the shunt, through the shunt, and then there's a piece that curves back around, which is this cable that you see running down through here, and then up to the negative side of the switch panel, or I'm sorry, pardon me, the fuse panel. And so we're ready to start wiring the individual circuits for the plugs that we need. And we're getting ready to wire the first of these. This one actually I think is the USB outlets for charging of phone, laptop, whatever. And it came with a nice set of leads that also has an inline fuse. We actually don't need that because, of course, we have our fuse panel. So thankfully, the geometry works out so that I'm going to snip this, attach a ring connector, and hook it to this first positive output on the fuse panel. And then the negative, I'll cut it just a little bit longer so that it can kind of make the corner here and then come back up and attach to the, negative section of the fuse panel. And of course, we don't want to leave a lot of extra cabling up here. We just don't want to create an opportunity for things to get pinched as we close it. We'd rather, I don't want to be tight, but I don't want it to be lax in particular. So. Okay, we have finished up the wiring. I've got all my plugs wired and connected, as you see, and then they head around the corner to the fuse panel. I'll pull the battery wiring out of the way. You can see we've got our panel all wired up, looking good. One thing that, one error that I made, one mistake I made was this. I talked about leaving space for these things with regard to placement of the shunt. I forgot about these, so that's one of them things. Turns out it's okay, but it ended up being a little tighter fit than I wanted to. So, and the other issue that I noted is it looks awesome when it's open, of course, when I was working on it, and then I realized like, oh man, when I close it, where's all this wire gonna go? And so I think we're gonna be okay, but that is one issue that I didn't really figure in too well. But again, I think it's going to be okay. So here in a second, we'll plug in the battery and see if we can release any smoke from this thing. Okay, we have the battery in. Everything's working great. I tested the USB ports. They're working great. I tested the cigarette lighter port. It works awesome. And now let's take a look at the power pole out. Let's see if they'll do what we want. Perfect. And let's see how we do here. Man, it's working great. I could not be more excited. I will edit in some footage of the Bluetooth app that goes with the shunt. I think it'll be a huge help. This is the app that connects to the shunt. It's fetching information via Bluetooth. We have 100% state of charge and basically a full tank of gas. Our voltage is 14.43 volts and no current draw. The charger for the battery is connected at the time this was captured. If we go to the history section, we have some interesting statistics. The most I've ever pulled off the battery between charges is 16 amp hours. The cumulative amp hour pull is 47. Lowest voltage 10.61, max voltage 14.44. If we look at the trends, you can see the various states of charge and discharge of the battery along with the voltage states over the last 10 days or so. Let's go back to status. We're going to disconnect the charger and apply a load. All right, so you see current and power flowing out. If we go to the trends and zoom in just a little bit, you can see a mild diminishment of the voltage, which is in blue, with the application of that load. Really appreciate you guys watching. Please realize that if this video is a little unpolished, it's the first video I've ever published. And yeah, who knows? We'll see, I guess. But please like it. If you don't mind, please don't subscribe, because then I'll feel like I have to make more videos. But in any event, thank you again, and have a great day.